Hello, welcome to my poster presentation. My name's Max and I'm a PhD student at Vehicular Systems. The purpose of my research is to provide industrial partners with control-oriented models of electrochemical powertrains. The focus that I'm going to show now specifically is some work on implementing one of the state-of-the-art fuel cell models that we have found in the literature as a streamlined and reusable Simulink library. So this model is developed by the University of Michigan, and we have used the data that they present online. We have implemented their model as a Simulink library, and now I would like to show you some of the results of that. So if you take a look at the components here, we have first compressed hydrogen stored in a tank. So this hydrogen is usually between 350 to 700 bar of pressure. So we need some sort of valve to maintain a reasonable pressure in the supply manifold. And after the supply manifold, we have a humidifier that's designed to enrich the dry hydrogen gas with water vapor. And this is done so that the membrane down at the fuel cell can transport protons efficiently. So after the humidifier, we have a mixture of hydrogen and water. And so the mixture enters first a gas diffusion layer, and then the hydrogen reacts here close to the membrane. And the membrane is also the electrolyte in this case. So any hydrogen or water that is not used in the reaction flows down to the return manifold. And then here we have a purge valve, which is normally closed. So this produces a restriction here. And so eventually we might get too much water in the gas diffusion layer. And at that point, we can open the purge valve to discharge the water, but also, unfortunately, also some hydrogen. So that was the anode side. On the cathode side, things are a little bit simpler. We have atmospheric pressure air coming into the inlet after some sort of filter normally. We humidify that gas as well. And then any oxygen in the air that is not used is just expelled out to the atmosphere again. Now, the problem with having too much water in the gas diffusion layer is shown here in figure 2. So the phenomenon that happens is since the most of the proton exchange membrane fuel cells are operated at 80 degrees Celsius, water is in a vapor liquid equilibrium state, and therefore we're going to get liquid water in the gas diffusion layer. And this is not very good because we have these droplets that develop at the gas diffusion layer surface. And so what happens is that when hydrogen is supposed to diffuse through the layer, we get blockages basically. So effectively we are reducing the gas diffusion layer area, or the fuel cell layer, the fuel cell area. And here we can see the effect of this in the data. So here we have measured output voltage as the red line and the model prediction as the blue. And we can see that we have a sharp rise in voltage when we open the purge valve. So when we open the valve, we discharge a lot of liquid water. So the liquid water blockage that's on the gas diffusion layer reduces, and we get a sudden increase in voltage. And this also means an increase in efficiency. And then after that, we get a slow decrease in voltage when the water builds up again. And then we open the purge valve again. And this causes this zigzag pattern in the voltage that the model that we're using captures pretty well.